Hey everyone, Amin here with AI Plays. Today we're covering dead pixel concealment. Let's get started. To recap from the previous video, we saw how visible light is captured by a camera, strikes a CMOS sensor, and is turned into a black and white checkerboard pattern image called a Bayer domain image. I did say that cameras usually have sensors with dimensions 4096 by 4096 pixels. That was a mistake. Camera sensors are more along the lines of 1280 by 1024 pixels in size. Regardless, such a sensor is very big, with over 13 million pixels. What if some of these pixels are broken? Dead pixel concealment is a method to automatically identify dead pixels and adjust their values using the surrounding pixel information. There are three different kinds of dead pixels: dead, stuck, and hot. Dead pixels are pixels that are simply not receiving any light at all. This can often occur when there is an issue with the lens of the pixel, or something is blocking the light from reaching the semiconductor. Stuck pixels are pixels whose values are stuck at a certain voltage value. This can occur when there is an issue with the voltage reader. Hot pixels are stuck pixels where the pixel is stuck sending the maximum signal, resulting in a full white. One method to detect problematic pixels would be to take a completely black picture, maybe with the lens still on, and a completely light picture, maybe of a bright bulb. Then you could correct any pixels that produced unexpected results in either case. This works since dead and stuck pixels are issues with hardware. Unfortunately, this method also requires that someone individually test each and every camera, which is just not practical. We'll use an automatic method of dead pixel detection. We do this by comparing a given pixel, called P0, symbolized by the P0, with all of its neighboring pixels, P1 through P8. If the absolute value of the difference between P0 and P1 through P8 is ever greater than a certain threshold, often about 5% the maximum intensity, it means that the pixel P0 that we are currently looking at is an anomaly amongst its neighbors. Since each pixel is so small, we can assume that a major anomaly suggests a dead pixel, else P0 is deemed not a dead pixel, and we can move on to checking the next pixel. This method works well for general dead pixel detection, but what about at the edges? If P0 is at the first pixel at the top left corner, it wouldn't have much of anything to compare it to because it doesn't have a full set of neighbors. To address this issue, we use 2x2 reflect padding. For now, we'll just look at the top of the image as an example. First, we can draw a line through the first row. Then we reflect the second and third row on top of the first row. This is done all around the image. Also notice, the corners reflect diagonally. Once you've identified which pixels are dead or stuck, it's time to correct them. One method is to just take an average of all the surrounding pixels. So add up P1 through 8, divide by 8, and set that value as the new P0. This method works fine in general, but what if your current pixel P0 is at an edge of a shape? The brightness intensity of the pixel on one side of the edge is going to be vastly different than on the other side, resulting in a skewed average. If you use this method, it'll dull the edges of your image. To address this issue, we use a gradient-based correction technique. First, we calculate dV, dH, DDR, and DDL. These terms just mean the change in intensity on a vertical, horizontal, or diagonal axis. The formulas for each are written on the side. The purpose of finding these values was to identify which one was the minimum and run calculations for the new value of P0 from there. Why is this important? If dV is the least of the four, it means that the intensity of the pixels changes the least along dV. So dV must be along the edge. Therefore, if you set P0 as an average of P2 and P7, the edges of the base image will remain crisp and undamaged by skewed averages. The method we covered works just fine. There's just one further simplification we can make, since we're just using dV, dH, DDR, and DDL for testing minimums. First, you can remove the 2 times P0 term, since that's the same in all four. By factoring out a -1, you can then change this term to P2 plus P7. Both of these are positive values by definition, so the absolute value is now unnecessary. Next, adding 1 to each of the four terms won't change which one's the minimum, and neither will dividing each by 2. This series of operations leaves you with this new set of dV, dH, DDR, and DDL. Now the minimum of the four is also the value of P0. For example, if dV is the minimum value, you can set P0 equal to dV. Now it's time to look at how dead pixel concealment would work in code. First off, I'll show you how you can access the files and image I'll be using. You don't need a super powerful computer or a long, confusing installing files for this. All you need is a Gmail account, and since you're here watching this video on YouTube, I'm assuming you got that covered. Now in the video description, I have included a Google Drive link. This is a link to a Drive folder that contains the raw bare domain image I'll be using. If you want to follow along, I suggest you download it. Next, to access the compiler, go to the search bar in Google and type in Google Colab. As you can see on screen, this takes you to a working compiler from Google, and it has various libraries like NumPy and Matplotlib pre-installed. On the left, you can see this File button. When you click it, it says you need to start a runtime to upload files. To do that, just run any script, even a simple print statement will do. Now you can press this button to add files. Add the bare domain image called colorchecker.pgm. Now you'll be able to follow along. The code I've posted on GitHub, also linked in the description, was written in Google Colab as well, and you're more than welcome to use it as you see fit. Now to the actual code. We start with the imports. We'll be using NumPy, a library for matrix operations, for the bare image transformations. Then we use skimage to read data, and Matplotlib to render the image. The bare image I'm using is in RGGB format. We also store the information as a NumPy array with dtype uint16. uint16 stands for unsigned 16-bit integer, so you can have positive and negative values. The maximum value in this array is 2 to the power 16 minus 1. That's 65,535. The minimum value is negative 2 to the power 16 minus 1. This is done to ensure no information is lost when reading the image or performing transformations. On that note, here's the important NumPy functions we'll be using. We start with this array under the variable x. We use the np.pad command to specify that we want to use 2x2 reflect padding on x. Take a moment to pause the video and confirm that reflect padding worked as you expected it to. Next, you should be aware that subtracting one array from another works element-wise, and so do inequalities. Finally, true has the numerical value of 1, and false has the numerical value of 0. By taking np.sum of an array holding true-false values, you can count how many true values are in the array. Now let's take a moment to preview the image. This image is what is called a color checker. It looks very similar to a makeup palette, and each square is a different color. It's great for testing the effectiveness of our pipeline. Also, you can see from this top leftmost 50 by 50 portion that the image is in the bare domain. Now we can finally start coding the functions. Let's start with the mean filter. It takes as input the raw bare image and the threshold used in dead pixel correction. We create the variable rows and cols to store the amount of rows and columns of the image. We then pad the bare image and create a copy of the original bare image to be edited and returned as the corrected image. Then starting at the third row and third column, or the first pixel in the original bare image, we start with the dead pixel correction. We'll label P0 through P8, and then create an array for the neighbor pixels, that's P1 through P8, by taking the absolute value of the difference between the neighbor array and P0. We have an array that stores information on how different P0 is from the rest of its neighbors. If a pixel is declared dead, then we can correct it. To do so, we just take the average of the neighboring pixels and replace P0 in the DPC image with the mean value. To take the average, we use np.sum over the array and then divide by 8. Here you can see the results of running DPC on the chunk of bare image. Notice we set the threshold to be 5% of whatever the maximum value in the chunk is. The results are not very visible since generally there aren't that many broken pixels, and the chance of finding one in this specific chunk is quite low. Also, here's the results of running DPC with the mean filter on the entire bare image. It takes about a minute, and you can see that it doesn't have too significant results for about the same reason. Gradient-based filtering works the exact same right up to detecting dead pixels. Once a dead pixel is detected, however, we define DV, DH, DDR, and DDL with our modified formulas. Finally, we set P0 in the DPC image to be the minimum of the 4 with np.min. And lastly, here are the results of running DPC on the chunk of bare image. Again, no major results since CMOS sensors generally don't have that many defective pixels. You can also see it works about the same on the full image. That's it for today. Next time we'll cover black level compensation. Have a good day, everyone.